Okay, so anyways, many of these terms probably somewhere in like physical science in middle school possibly. You may have heard some of these, especially in Newton's laws. But at that level, it's mostly kind of shaved down, cut down versions of them to make them sound a little simpler. It's not that they're that hard, but they're probably a little more technical sounding now. So Newton's first law has a couple things involved. Like basically, I would say 3 big parts of it. And one thing Newton's first law tells us is that objects at rest stay at rest. Now, in a more elementary version of it, the next part sometimes isn't stated clearly enough. You probably heard it as objects in motion stay in motion, but just saying that really isn't good enough. Because what it really means, how it's stated on your definitions, it's a little more specific. Let's see how they put it here. It said an object moving will continue moving in a straight line with what? Constant speed. All right, so, or we could condense that. That's the way it's written in the back of the book. Straight line means not changing direction, right? And if you're not changing direction and your speed's staying the same, then that would also mean the same thing as constant velocity, right? So basically, so far, to kind of sum all that part of it up is things do want to stay at rest that are at rest. Things do want to stay moving the way they're moving at constant velocity unless acted upon by what? Nope. More general than that. A what? A force. But again, we got to be a little bit more specific. In our definition, it ends with if and only if the net force acting on the object is 0. I'm going to use a different term for now because net force is one of our words we'll get to, one of our other definitions. But we're going to say unless acted upon by an unbalanced force. All right. If you just say unless acted upon by a force, we're going to see why that's not true in a second. All right. So that all together, that whole thing is Newton's first law. And it tells us a lot of really common sense stuff when you think about it. So let's take an object at rest, like this bowling ball. That doesn't want to move, right? Things won't Another way to briefly sum up Newton's first law is things don't magically want to accelerate. They have to accelerate due to an unbalanced force, all right? So if something's at rest, is it accelerating? No. If nothing ever comes up and applies an unbalanced force on this object, it's never going to move, all right? Now, what do I mean about unbalanced force? Well, I guess let's talk about balanced force first. Let's identify what forces are acting on this ball. Now, force itself, just a plain old term force, what was the definition? A force is pretty much just defined as any what or what. Who remembers? Look if you don't remember. Any what or what? Krish? Nope. Push or pull. And they do have direction and magnitude, so they're vector quantities. Okay? So, let's try to identify all forces that are acting on this ball right now, because there are some. What's one force acting on this bowling ball right now? Charlie? Gravity. All right? The force due to gravity is also known as the weight of an object. All right? While we're doing this, up on the board, I'm going to draw. And all these terms kind of fly together. That's why we're not just defining them one by one in any particular order. There was another term, free body diagram. All that means is a diagram that, I keep moving my thing here, a diagram that shows all forces acting on something. So here's my table, here's my bowling ball. If I draw a free body diagram from it, where do you think gravity always points? Since forces are vectors, we could draw them with arrows. Where does gravity always point 100% of the time, Charlie? Down. Directly down. Even when we get in a few weeks to inclines and hills, it still points directly down. All right, so we're going to draw one force vector that represents that. And usually when we name vectors, give them a variable and their forces, usually we write like F, then a subscript that narrows in what kind of force it is. So F sub g means force due to gravity, but this is also known as weight. I'll just write that up here. Just pay attention. You don't have to go write this right now. Just pay attention. Get used to those two terms being used interchangeably. Force due to gravity and weight. Now, are there any other forces other than gravity acting on that bowling ball right now? Yes or no?
Well, because it's like pressing down on it when the table.
Exactly. The table's got to be pushing back up on it. And that's another one of your terms. This is a perpendicular force of a surface pushing back on something else. What was defined in your terms as that? The normal force. Good. The normal force is basically the reason why this thing is not falling through the table. So right here is one reason why some elementary versions of Newton's first law aren't quite correct. Objects at rest want to stay at rest unless acted upon by a force. If you just say that, that is wrong. Because this object is at rest, and there are two forces acting on it, right? So one way we like to say it is unless acted upon by an unbalanced force, or a force that has a net, a total, that is non-zero, I think is the way your book defined it. That all means the same thing. So when we get amounts of forces involved, when we bring the math in, I'll just make up some numbers. By the way, does anybody know what the metric unit for force is? Yeah. Say that a little louder. G grams? Is that what you say? Looking for a unit. Grams is a unit for mass. Newtons. All right, we'll get more into that later, but just for some example numbers. Let's say this bowling ball weighs 50 newtons, okay? If it's pushing back, if it's not moving, if it's pushing on the table with 50 newtons of force, how much does the table have to push back to keep it not moving? 50 newtons. They balance, all right? So this is following exactly what Newton's first law is saying, that something at rest will stay at rest basically as long as the net, that means total amount of force on it, is zero. All right? If all of a sudden one of these two forces becomes greater than the other, in this situation that's unlikely, but let's say this is an extremely heavy object, and maybe this table just isn't strong enough to support it. What might the table do? Break. And if the table breaks, that means it can't provide a normal force back on you. All right? You guys are all being affected by a normal force right now with your seat pushing back on you, right? Whatever you weigh, now in English Standard Units we're used to pounds, right? But whatever you weigh in pounds or newtons, whatever units we're using, whatever that number is that you're pushing down on your seat with, your seat has to push back on you with that equal amount. And if it can't happen, that means you will fall through your seat. All right? Now, the next thing is the other part of Newton's first law was, we said objects and moving at constant velocity want to stay at constant velocity, right? Now that one's a little bit harder to easily show, especially on Earth, where there's a lot of resistances. But it's not that it's not true, we just need to think about it. So, I'm the bowling ball over and go over to this thing. I'm not going to turn it on yet though. Here's an object. I'm going to put it moving at constant velocity, and then I'm going to let it go. So I'm going to slide it for a moment at constant velocity, then I'm going to let it go. Wait. Newton's first law just said objects moving at constant velocity want to stay at constant velocity. Is Newton wrong? No. So why didn't that seem to follow it? Yeah. Friction. Friction, once I let go, provided an unbalanced force. I'm able to slide this thing at constant velocity because I could continually provide a force that opposes friction. And it's, in essence, balance it out. So this thing will move, but when I take my hand away, since there is friction, it pretty much immediately stops, doesn't it? Because that friction, without my hand still being there, is an unbalanced force. It's a net force that is non-zero, and it brings it to a stop. So it actually is following exactly what Newton said. All right. Why I use this thing is because I can essentially make friction, not make it zero, but make it so low it's basically insignificant. It's just a little hovercraft now. So if I do the same thing now, and essentially have friction turned off and I let it go, it looks like it's moving how? Constant velocity till it hits something, right? So all that together, things will only stay at rest and things will only stay moving at constant velocity unless the net force is equal to what? Zero. Or another way to say that means the same thing, unless an unbalanced non-zero force comes into play, which when there was significant friction it did. Now another term that goes along with all this was inertia. Sometimes Newton's first law is also known as the law of inertia. Who could tell me what inertia is without looking? Anybody have any idea? Because we've all probably heard that term before. Yeah. Kinda. Any others? All right. All objects want to follow what we just defined in Newton's first law. But some objects seem to want to follow it more than others. So let's go back to the bowling ball. I need a quick volunteer. All right, come up here, Ashlyn. All you got to do, this is why I get a volunteer because I don't want to hurt myself. I want you to flick that bowling ball as hard as you can with your finger.
Flick it?
Yeah, just stand to the side so everybody could watch nothing. Did that hurt? Good, sit down. All right, so she provided a force on that bowling ball, right? Everybody agree? Now, it didn't go anywhere, though. I'm going to pretend I flick it hard. I'm not going to do that because it's going to hurt my finger. All right, but since I have provided a force there, it should want to try to move. But there's still what between it and the table? Friction, all right? If there were no friction, we could probably all agree it would have moved a little bit, right? But probably not accelerate that greatly, right? Because it's pretty what? Heavy. It has a lot of mass, at least compared to maybe this ball, right? So now I'll do this one. I don't mind hitting this one. I'm going to flick this with, probably close to the force that Ashlyn did the bowling ball. And when I flick this one, it flies across the room, right? Now both of those balls before we flipped them were at rest, and they both wanted to do what? Stay at rest. But which one wanted to stay at rest more, obviously? The bowling ball. Why? Because it has more mass. So anyways, inertia, as defined in your terms, is the tendency of an object to resist change. All right? What kind of objects tend to resist change more? Objects with more mass. It's not that this one doesn't want to follow Newton's first law. It just doesn't have as much mass as maybe another object, and when an unbalanced force comes along, it will do a lot more to it than compared to that unbalanced force on a much heavier, more massive object, right? And we can flip it the other way. When I take this ball, this ball and whip it at people in here, nobody gets really scared because you know it's a foam ball coming at you. Charlie didn't even know the last second. He didn't even flinch. Either that or he was sleeping. So I think it would be a lot different reaction if I picked up this bowling ball and threw it at somebody. Oh, don't hit that. Okay, that's it. I'm okay if it hits your book back. I just didn't want it to hit back right there because sometimes I put dents in this. But if I threw that bowling ball directly at somebody, you probably wouldn't sit there just like this, like, right? Both of them were objects in motion after I released them, right? You could walk that up. I really don't trust your throws. Actually, if a few of you would get on the hallway in a triangular arrangement. And okay. But anyways, both of these were in motion and both wanted to stay in motion. Which one obviously wants to stay in motion more? This one, right? And specifically in motion at a constant velocity. So if you were to get in front of either one of them, it wouldn't take a whole lot of heck of a force when it hits you to stop this one, right? But it would to stop this one, right? So this one, again, has more inertia. If it's at rest, it wants to stay at rest more than this one. If it's in motion, it wants to stay in motion more than this one, right? So that's basically Newton's first law, and that's why it's called the law of inertia. It kind of explains what inertia is. Excuse me. Hello? That's okay. Yeah, sure. But they have a loaner Chromebook you can go up and get. All right, so just to recap a few things. So now we know what inertia is. It's a tendency for an object to resist change. And we got to remember it's tied to the mass of an object. The more mass, the more inertia. The less mass, the less inertia. Newton's first law, we just said it a bunch of times. This was called what kind of diagram? Free body diagram. All free body diagram is depicts the force, all forces acting on a single object. And forces are pushes or pulls. And in addition to the definition for forces, or force, it also said these forces could be contact or field forces. All right? Contact force kind of describes itself. A force that literally has to make contact with the object. Like for me to put a force on this bowling ball, I have to literally make contact with it, right? Because I don't have the force, right? I can't just be like, go, move, right? But there is a force that we just described that does act like that. Not air. Air literally contacts it. Yeah. Gravity. Gravity didn't come up, put up a hand and pull that ball down, right? Gravity is what's known as a field force. Now in mechanical physics, probably the only field force we really study closely is gravity. And one thing that's true about all field forces is that as you get further away from the source of gravity is the Earth, right? As you get further away from the Earth, what happens to gravity? It gets smaller, weaker. Just like other field forces that we're probably at least a little bit experienced with, magnetism. Magnetism is a field force, right? You get further away from a magnet. Is it as strong as it was when you were close? No. But in this course, probably the only one we'll get into any detail that's a field force is gravity. All right, so moving along then, so we get through most of these. Newton's second law. This is going to be really, it's an ugly definition. It's a wordy definition, and I'll just read it straight from your definitions. And you remember I told you in some of these we might add something to your definitions? We're going to add something to this one. It says, it states that acceleration of the object is proportional to the net force and inversely proportional to the mass of the object being accelerated. What the heck does that mean? If you ever try to say an equation in words, it's always ugly. All right? But that's really just stating a simple equation that we're going to use a ton in like the next 2 months. All right? So somewhere near where you have Newton's second law written, the definition, wherever you did your vocab terms, add this to it. It's really stating a formula. F net equals MA. That's really what that's saying. That looks like a pretty simple formula, right? It is, but as we get further and further into forces, what's on the left side of this equation could encompass a lot of different forces. Remember, a minute ago I said net means the same thing as what, guys? So a couple times earlier. Net means the same thing as what? Total of all forces. All right? So if there's only one force acting on an object that we're doing a problem with, then that is the net force. But in many cases, there's more than one force acting on objects. Okay, not all the time, but many times there are. So then, if there's 10 forces acting on an object on a particular axis, then there might be 10 different variables up here. We're not going to have problems that crazy. But I'm just saying, for example, there definitely could be. All right, so this little equation could get kind of big quick. But in some cases, it really is that small. And that was one of your vocab terms, I believe, as well, right? Net force. And by your book definition, net force is the vector sum of all forces acting on an object. But sum means the same thing as total, right? The total of all forces acting on an object. There's more specifics to that when we start getting into problem solving, but for now, that's all you need to know. The net force is the total of forces acting on something. And we show that on free body diagrams that we just spoke of. All right. So that's Newton's second law. Make sure you write that by the definition. It's all that ugly definition really is saying that formula right there. And if we think about it, it's pretty much as common sense as a formula could get. If we want to take a mass, I don't care what it is. This is anything that has mass, m, right? And by the way, there's no variables for inertia directly in this formula, but it's represented through mass. Remember, things with more mass have more inertia. So there's m, mass. Your amount of mass really determines your amount of inertia. It's basically the same thing. So if you want to take a mass and accelerate it, you have to apply a what? Force. And the force, if it does accelerate, has to be a non-zero net force. Because if net force is zero, then we have a case called equilibrium. That's another one of your terms. And equilibrium is the condition in which the net force of the object equals zero. Equilibrium just means net force equals zero. All right? If the net force equals zero, meaning we're in equilibrium, that means one of two things is occurring. It's either at rest or moving how? Constant. So when we say something is equilibrium, one misconception is that too many students often just think, well, if it's equilibrium, you have to be at rest. No, you just have to not be accelerating. If you're at rest, you're not accelerating, right? And if you're moving at constant velocity, we've already learned that you're not accelerating, right? A equals zero. So all this stuff like comes and wraps into each other. You know, stuff we learned in the past as well. All right, a few other things before we go into another force or another Newton's law. Make sure I didn't miss anything that I wanted to talk about yet. Okay, so let's move on to Newton's third law. Another one which I'm sure you've heard, just might be a little more technical sounding. The general way to say it is usually for every action there's a equal and opposite reaction. How many of you have heard that before? All right, and it pretty much sounds similar to that, but the definition you guys had for the third law said all forces come in pairs. The two forces in a pair act on different objects and are equal in strength and opposite in direction. Means the same thing, just a little bit worded a little bit differently. Now, in this chapter, you need to know what Newton's third law is as a concept. Mathematically, we don't really study Newton's third law until later in the year until we get to momentum. Because actually later on down the road, something called the law of conservation of momentum is really the mathematical version of this. So right now, just need to think of it as a concept. So, real quick example of this. When we're discussing Newton's third law, there's always two objects involved. And we call them an interaction pair. That's another one of your terms. All right? And the pair in this example, we've used this a lot for a lot of things, right? Is the gun itself and the dart inside. And it doesn't happen much on this because it's just a dart gun, but let's pretend for a second this is a real gun. If you pull the trigger and fire a real gun, what's it going to do, at least somewhat significantly? I exaggerated it there. It's going to kick, recoil, right? And that's a good example of this. All right? Basically, there's one force that occurs when I pull this trigger. It's a burst of air. In a real gun, it's rapid expansion of hot gases, right? And it pushes on the gun itself, which I'm holding, and the bullet, right? So there's your equal and opposite reaction. All right? That one force, that action, created an equal and opposite reaction on the gun moving this way, on the bullet moving that way. And we could use a term we just learned to understand why the bullet moves so much faster than the gun. The same force was put on both of them when you pull that trigger, right? That same burst pushes on the gun and the bullet. Why does the bullet go flying out so fast? And this, even if it kicks back pretty hard, depending on the caliber of the gun, it's not going to rip your arm off, right? Why? Why does this not travel backwards nearly as fast anywhere close to the bullet? Yes? Exactly. It has more inertia. Or in other words, it has more what? Mass, right? So that big force could accelerate something with low inertia. Both were at rest before I pulled the trigger, right? But that force became an unbalanced force once I pulled the trigger. That flew out the little low mass, hence low inertia bullet, real fast. And since I'm holding this gun, I'm like part of it basically. So not only the mass of the gun, but my arm and everything holding it is like all one mass. And that's a lot heavier than that bullet, right? A lot more inertia, so we resist the change more than that bullet did, right? Goes out real fast. So the interaction pair thing has to do with that. By definition, the interaction pair said a pair of forces that are equal in magnitude but both opposite in direction. That would be the one on the bullet versus the one on the gun. Another simple example of this is just something we do, little things we do all the time without even thinking. Simple walking is a great example of Newton's third law. I push this way, but the floor pushes me which way? That way. That's an interaction pair right there. I put a force on the floor this way to walk forward, but it pushes me back this way. Mainly because of this between my foot and the floor. Friction, right? If there was no friction between my foot and the floor, would that happen? I'd push off and I'd just stay there because there'd be no friction there. So friction sometimes is a bad thing in some cases, but a good thing in another case. In mechanical systems, friction often creates what? Like heat. And heat is bad for mechanical systems, but the friction involved in like walking or moving and stuff like that is not a bad thing. It couldn't happen without it. Friction we talked a lot more later. All right, so there's a quick summary of and some examples of Newton's three laws. Now there's some other ones. I got a few minutes here to hit on that we didn't talk about. Let me see which ones we didn't get to yet. Some specific forces. We already said normal force. Normal force is when a surface pushes back on something else, right? Like the floor on you, your seat on you, something like that. Even when I go over to a wall like this and lean on it. I'm not putting all my weight into this wall, but whatever percent of weight I'm putting into this wall is better pushed back on me with the same amount, otherwise what would happen? I would go through. So if this wall is providing a normal force on me this way, it's always perpendicular to the surface. The normal force is always perpendicular. That's part of the definition. All right, there's some other forces in here that will come into play a lot. Tension is one of them. We all know that term. But what do you think of when you hear the word tension? Okay, you're thinking surface tension, which, yes, could be. I'm looking for something else, though. Yeah. Right, a string, a rope, a chain, a cable, anything you could give slack to and pull tight. All right? When we have strings, ropes, chains, cables, or anything like that involved, we call them tensions. All right? So when we draw free body diagrams more often later, once we get into some problems, anything like that, we'll call it a tension force. That's about all there is to say about that right now. All right. Another one we have here is a drag force. Give me an example of a drag force. Then we'll read the definition. Yeah. Yes, a parachute. What pushes on the parachute to create that drag? The air. Air resistance, which we have talked about at times in here, right? Air resistance is a form of a drag force. Why? Because by definition, a drag force is a force of a fluid on something as it goes through that fluid. And air, yes, it is a fluid. Any state of matter that can flow is considered a fluid. All gases can flow, right? So all gases are fluids and all liquids are fluids. Anything that can flow. So anytime something's going through a gas or a liquid, the force of that gas or liquid or fluid in general that resists it going through is considered a drag force. Okay? And speaking of that, we did free fall, and we ignored drag forces then during free fall, didn't we? Right? But if something falls in, we can't ignore air resistance. If it's present and significant, will something that's falling with significant drag, significant air resistance, will it accelerate necessarily the whole time till it hits the ground? No, it won't. This might in this room. This is a small fall. But this ball doesn't have much mass. All right, so from a pretty high fall, air resistance and the drag force could build. and get to a point at which it equals the weight of it. At that point, forces are balanced. Let's go back to Newton's first law. When forces are balanced, can we have acceleration? No. We have a term for this through drag forces, especially for falling. I could show it real easy with a sheet of paper. As a matter of fact, weeks ago we did. We just didn't focus on this fact. When I drop this sheet of paper, it looks like it just floats down to the ground, right? Because it has such a high surface area and a lot of drag force could catch it very quickly, it basically barely accelerates. It floats on down like mostly a constant velocity, at least until it gets to the side and changes form, right? It floats for a while pretty steadily, doesn't it? We call this terminal velocity. And that's another one of your words. Terminal velocity is when something is falling with significant air resistance, and the force of air builds up enough to equal the weight of the object. When that occurs, acceleration stops. Now be careful how you take that. When I say acceleration stops, does it stop in midair? No. It stops accelerating and moves at what kind of velocity? Constant. All right? So, some things, though, that are very aerodynamic, that might never occur with, right? Some things that cut through the air that don't have much surface area and maybe especially have high mass with not much surface area, that may never happen, even with air there. But objects with big surface area, especially with low mass compared to that surface area, will reach terminal velocity very quickly. And I don't know if we brought this up in the past, but even if we did, it's relevant now. Did we ever bring up the idea like an ant or insect flying off a windowsill? Did we talk about that in the past? Okay. So we've all probably seen it happen before. Like maybe like flipped a little bug or something, maybe the size of an ant, whatever, and saw it fall from a pretty high height. And then it hits the ground and scurries away, right? And did you ever wonder how that's possible? Because if we took any of you up to even a moderate height and dropped you, you're probably not scurrying away, right? If we took you up as high as only the ceiling and dropped you, you're probably in trouble, aren't you? Right? Why, if we took an ant to the ceiling and dropped it, is it just going to simply scurry away and be fine? Yes?
There's less mass.
Well, it does have less mass, but that's not the whole story, right? There's two things. I'll give you that as one of the two things. It has low mass, and the other one's kind of maybe hard to get if you never learned it or thought about it before. And before you say, what? Just hear me out a second. An ant has a high amount of surface area. Wait a second, that doesn't make sense, right? They're this small. They have a high amount of surface area compared to their mass. All right? We call it the surface area to mass ratio. If you have a high surface area to mass ratio, that means anything that does, it will reach terminal velocity like that and essentially look as if it floats on down to the ground. We don't. We have a very small difference of the surface area to mass ratio. So if we fell from that same height, well, guess what? We're accelerating the whole time till we go splat. Okay? So it's not just one or the other. It's two things. You have to have a high surface area compared to your mass. That doesn't mean a high surface area in general compared to the mass that you have to reach terminal velocity very quickly. And that's why things like that happen. We might expand on some of that and some other questions like that in the future. But I think that covers, I just wanted to at least get to some examples of all this stuff rather than this being straight up definitions. The only one we didn't cover then was weightlessness. It says, for the definition of weightless, an object's apparent weight of 0, and then speaking of that, that's the other one, apparent weight and weightlessness. They kind of go together. All right, your weight, whatever it is, let's say you're a 200-pound person, all right? That is when you are in equilibrium. You feel 200 pounds, all right? How many of you have ever been on especially like an amusement park ride, like a roller coaster, and felt like you were heavier, all right? Or even in something less, to a lesser extent. How many of you ever were in a elevator and felt heavier, like you were forced into the floor a little bit? That's called an apparent weight. We will do many problems with this. Because apparently, because of acceleration, you could feel heavier than what you really are. All right? So apparent weight, by definition, is the force an object experiences as a result of all the forces acting on it given an acceleration. So if you're not in equilibrium, if you're speeding up or slowing down, you could feel heavier or lighter than what you really are. So that's what that basically means. And if it's to the extreme, you could feel weightless. So that's our last term today to discuss. Weightlessness actually is not a great term because it's not necessarily accurate. You could feel weightless, but there's no such thing as being weightless. When you hear about weightlessness, what may pop into your head? Maybe an astronaut, right? Weightless in space, but they're not. They're in orbit, and orbits are caused by gravity. And if there's gravity, you can't be weightless. But last thing for today, real quick. Let's pretend you're standing on a bathroom scale like this. And if you're a 200-pound person, you look down, it would read 200 pounds if you were at rest on the ground with it, right? But let's say you and this scale were falling. And you look down. What would the scale read? Scale's under your feet and you're falling. You and the scale. What would it read before you leave? Could it push back on you if you were both falling? No. So what would it read? 0. You would feel like you're weightless. But there you would definitely have weight. So weightlessness is really an apparent feeling of 0. All right, so make sure you study these terms tomorrow. Again, you get a word bank, and all of them we'll get into a lot more detail with. This is just a quick introduction to all of them.